So then today we will finish this two-dimensional Ising model by renormalization group analysis. There are remaining topics about the RG, for example, this momentum shell RG and the finite temperature, finite size effect, crossover, scale, and so on, which we cannot cover this semester. And also the costly solids transition. But today we will finally finish the RG for 2D Ising model on triangle lattice, which was studied by Onsager long time ago by exact methods. But now, using RG, we could more or less reproduce this exact results, but not in a precise way, but more or less, approximately. Again, so this is the lattice, Ising model on triangle lattice, and by RG, we mean we first perform the cross-grant average over each individual block spins on the partition function as we defined already. Then we try to find out this H prime or the effective Hamiltonian in terms of the block degrees of freedom as capital I here. And by partially summing over the microscopic degrees of freedom within each block, and we could get this H prime. And for example, the definition of this as capital I within this block unit, and it is defined by this majority rule. We know that for each triangle, there are 3 spins, and each spins can take up or down values as the spin configurations. So altogether, there will be 8 configurations, and this is precisely written over here. There are 4 configurations corresponding to this as capital I being +1, another 4 being -1. The way that would identify this plus or -1 is by the majority rule. So if the sum of the 3 spins is actually positive, then this is +1. For example, 3 up, 2 up, 1 down, 1 down the middle, or 1 down in the first. So 2 plus spins and 1 minus spins gives you plus configurations. And likewise, if the majority of the spins are pointing down, then this block spin should also point down. Okay, so we can estimate this H prime by perturbation theory. Remember that we assume that our Hamiltonian after the block spin average has the same form as before, but that is just assumption. But we need to take this assumption that the Hamiltonian is given by the H0 part, which is simply given by the spin-spin interaction within the same block. And also there's a small perturbation, which we call this V. And this V describes the interactions between different blocks. So by doing so, we could actually decouple the contributions within each block or among different blocks. And of course, there will be higher order terms, but we don't consider this higher order terms here. Of course, you can imagine that there are second neighbor block-block interactions, which we don't consider here. And here, this is just nearest neighbor interactions as the leading contributions here. So we could find out what this effective Hamiltonian H prime is when we partially trace over the block spin. So by tracing over, we mean that we take the ensemble average of any quantity A by using this H0 as the zeroth order approximation of the Hamiltonian, and any observable such as a spin could be estimated by this method. So in other words, we could partially trace out the each individual block spins, and then we could use that approximation over there and to decompose this kind of a partition function into 2 parts. One is the trace within each block, another is the summation only involving different block spins. And then we could separate these two contributions, and this, when we multiply these two together, we get the e to the h prime, where h prime is exactly what we need. But then when we trace out each individual block spins, e to the h0 within each block, this is nothing but m's powers, where m is the number of blocks of this z0, where z0 is just a partition function of a partial trace within each block. And there are m blocks, so the total contributions for this summing over, partial summing over the individual block is given by z0 to the power of m. Okay, what is z0? Z0 is nothing but this e to the h0 with a partial summation over these three spins on a particular triangle. And the three spins of each individual block are coupled through this Ising term, S1, S2, S2, S3, and S3, S1. So if you simply just use that majority rule over there for, say, S capital I being plus 1, you get this contributions, e to the 3k plus 3 times e to the minus k. You can easily verify this by plugging these 4 configurations up here. And likewise, you could evaluate the z0 for this block spin being minus 1, which is the button 4 configurations. And you plug in these button configurations, you get to exactly the same results. Therefore, you could easily estimate the partial trace over individual block, and the remaining job is to estimate this thermal average with respect to the 0th order Hamiltonian of this e to the v term, and which we could Taylor expand this in terms of the expansion, which is 1 plus v plus 1/2 of v squared plus the higher order terms. And we could simply just separate these leading terms into 3 different terms. The first term is the trivial one, and the second term is the linear order in v with the ensemble average with respect to the h0. The second one is 1/2 of a v squared average with a subscript 0, and so on and so forth, and we neglect the higher order terms. And we can take a log and re-exponentiate, and we get the potential term contributed to h prime, which we will finish this after the short break. Let's finish the calculation. So we can estimate the h prime by evaluating this logarithm of e to the v with ensemble average respect to this h0, and we could actually Taylor expand this log and then re-exponentiate this identity here and to get h prime, and h prime now becomes this 0th order contributions of the block spin, degrees of freedom, plus the interactions between blocks, which has its 2 terms. The first term is just a linear in v, which represents the nearest neighbor block-block interactions, and the second term is actually the v squared term, v squared ensemble with respect to 0 minus v0 square. So it's a v squared 0 minus v0 square. So this is the second nearest neighbor, next nearest neighbor interaction. But we don't consider the second neighbor terms, just keep this first order a linear in v term. That's a nearest neighbor, a block-block interaction, and we could just get the recursive relations between k prime and k by considering this, calculating this v0. So how do we calculate v0? Well, v0 is simply just nearest neighbor block-block interactions, which could be demonstrated using this cartoon picture here. I use 2 triangles to represent the nearest neighbor blocks with 1, 2, and 3, indicating the associated spins on each individual blocks. And this v term is nothing but the sum over nearest neighbor block, capital I and capital J, of this Vij term, where Vij is simply just coupling between the nearest neighbor blocks? Well, the couplings are only two interactions in this diagram. The one is the spin on site on block 1 or block I. The first spin, the spin 1 on block I, interact with the spin 3, the third spin on the nearest neighbor block J, and the second term is actually 2, 3, where 2 comes from this block spin I, and the 3 comes from the block spin J. But this is just a symmetric, so the labeling 1, 2, and 3 are arbitrary. Therefore, these two terms should give us identical contributions. So then we simply just multiply this single term by factor of 2 here to sum over these two contributions, because these two are identical. So then we zero into just calculate the single term S1I and S3J with the ensemble average respect to 0. And because this S1 belongs to block spin I and S3 to block spin J, they are different separate block spins. Therefore, if you take the ensemble average respect to the block, and they should be decoupled. And therefore, we can simply just decouple these two spin correlations in terms of the product of the two single spin ensemble average. But what is the single spin ensemble average S3J? 0, by definition, is given by this partition function in the denominator over a single block, and within this numerator, it is just standard definition of the ensemble average, whereas Boltzmann weight is simply just these three terms, and we should multiply the Boltzmann weight by this S3J. And using the majority rules of this Sj, and for +1 configuration of Sj, you could easily evaluate this S3J0 as simply just this function phi k multiplied by Sj itself. And likewise, this S1I, 0 here, ensemble average, is given by the same factor 5k multiplied by Si. So you could combine these two and take the product of these two results. You get this V term, which is sum over nearest neighbor blocks, I and j, and inside the summation, it is the 2 times k times phi k squared times S capital I and S capital J. Remember, this interaction term is exactly the same form as the original Hamiltonian of the Ising model, and the only difference is that now the coupling constant changes. So k prime now becomes 2 times k times phi k squared. So now we get a recursive relation between k prime and k, performing the partial trace over the block and assuming that the interactions of the system remain the same after you summing over each individual block, and the block-block interaction is still nearest neighbor type. So now we could just analyze the fixed points, and by using the fixed point value on both sides of the recursive relation here, and there are 3 fixed points. One is at 0, which is a high temperature fixed point. Another is infinity, which is a low temperature point. And the third non-trivial one is at intermediate value of the temperature, which is at this value, about 0.34. And this value is very close to the Onsager prediction by the exact method, which is 0.27. And next we could just evaluate this exponent yt by using this definition that we defined earlier, that lambda t is actually the scale factor b to some power of yt, which is the partial derivative of this k prime respect to k at the fixed point value. And this is, this can be evaluated and can be compared with the exact result, which is really, really close, 1.62 for this RG and 1.73 for the exact method. We can use the same method to discuss the effect of external magnetic fields by using the same mapping, by tracing over this microscopic degree of freedom within each block, and we could actually get a relation between this delta H and delta H prime. And the relation is precisely this factor 5k. And along this field direction, there's just one non-trivial fixed point, which at k star c here, and we get this lambda factor in the field direction, which is 2.12, which is not far away from the exact prediction. So now we could just plot this global phase diagram by combining all these pieces together. So let me just stop here for a minute, and we could just sketch this RG flow and explain all these fixed points and the direction of the RG flow and so on. So let's take a short break. So let's just finish this discussion by presenting this global phase diagram of this two-dimensional Ising model on triangular lattice. As we discussed already, there are 3 important fixed points. Now, in fact, there are 1, 2, 3, 4, 5, maybe 5. But the most important fixed points are K star being 0, or high temperature fixed point, which corresponds to the paramagnetic phase. And also the K star being 0 is a high temperature paramagnetic phase, where the K star being infinity is a low temperature ferromagnetic phase. So these 2 fixed points are stable fixed points along the interaction coupling constant direction K, in the sense that the scale factor, or the eigenvalue along the temperature direction lambda t, is actually less than 1, is a half here for the ferromagnetic fixed point. So all the flows become irrelevant, meaning they're flowing towards the fixed point. Likewise, for the paramagnetic fixed point, the eigenvalues is again 1/2, which is less than 1, and therefore as we keep renormalizing this model, this coupling constant becomes more and more closer to that fixed point value. So that's called the irrelevant direction. But near this Kc, you get a relevant RG flow, in the sense that the RG flows are actually moving out of this fixed point value. So this is kind of a very unstable, and therefore this is a critical point of a two-dimensional Ising model on triangular lattice, which is at a finite temperature with the K critical value Kc being 0.34. So on the right side of the Kc, the flows are towards the infinity, which is the ferromagnetic phase, meaning if the temperature is less than that critical temperature, and the system will ordered, and it will become the ferromagnetic ground state. And on the other hand, if the temperature is above Tc, then you end up being a paramagnetic high temperature phase. So that's the zero field phase diagram. But in the presence of field, the field is always take the flows to this spin polarized phase, where the h is actually the y-axis, is either plus infinity or minus infinity as a fixed point value. Near this h star being 0, in the middle here, all the flows are moving away from that paramagnetic zero field fixed point. Okay, so in the presence of an infinitesimal amount of a positive field strength, and RG flow will take you to the plus infinity polarized phase. And on the other hand, for this tiny little bit minus negative field strength, the whole system will flow to the other spin polarized phase with negative field. And at any given finite temperature and field, the general RG flow follow this kind of arrow directions. You can start at any place in the phase diagram, and the RG flows will follow these trajectories indicated by these arrows. It may initially make a detour, but finally it will end up with being in the either one of these 4 fixed points values. And this is the RG analysis of the Ising model in 2D on the triangular lattice as an example of this powerful technique. And so our class and lectures end here. Let me just summarize everything we learned during this semester. So first, we studied the phenomenology of this phase transition, but we know from statistical mechanics that something non-analytic must happen. But we don't know how and why that happens, and we just study the thermodynamic limit, and we realize that this non-analyticity properties must happen in the thermodynamic limit, but how? And by using the Landau free energy formalism, we sort of know how this phase transition occurred and why that happens. But we still need the more systematic and reliable tool to actually understand all these predictions on the critical exponents and so on. So then we deviate from this Landau's mean field formalism by studying these Gaussian fluctuations. And then we still cannot get a more reliable predictions about all these exponents and so on. So therefore, we need to understand this physics from this renormalization group approach. But at the very end of this course, which I originally planned, I plan to tell you, another so-called epsilon expansion in field theory approach, where you could add this 5/4 term in this Landau's formalism to go beyond this Gaussian approximation. Okay, so once we include this 5/4 term, now things become interesting because now you could have other fixed points than just a Gaussian fixed point. And this non-trivial fixed point called Wilson-Fisher fixed point, which describes the phase transition near upper critical dimension, which is 4. And using momentum shell RG, which is the complementary approach to this real space Bloch spin approach. So we are able to integrate over the high energy modes, and we could get effective Hamiltonian in terms of the low energy, low momentum theory. Again, and we can trace the coupling constants while we map the system to the coarse grain version or low energy version. And then we could solve this RG scattering equation and find the fixed point value and get the eigenvalue and exponent and so on. So that kind of discussion is actually missing at the very end of the course, and I plan to provide you with more details in the future. So to summarize, by now I hope you get feelings of what this phase transition is about and how to understand this phase transition in terms of the statistical mechanics principle and the thermodynamic limit, and use the eyes from the renormalization group perspective. You can understand this phase transition critical phenomena in a more accurate and precise way. And this phenomena happens in all areas of solid-state many-body systems. And this phenomena is really interesting, exotic, and mysterious, but understandable at the same time. So then I hope you enjoyed this lecture and course and the study and this textbook, and I'll see you on next Monday for the final exam. So I hope you do not forget to fill out this questionnaire, the query questions, to actually give me some feedback on this course. And thank you for your participation and hard work on this homework. And I hope everyone get a good feeling about this course and also the good grade. Okay, so I'll see you in the future. Okay, bye-bye.